Hey, welcome back. So this is part two of my series on diffraction for physics and as a foundation for AP Physics classes as well. In this lesson, we're going to be talking more about the double slit experiment for waves, how to do diffraction problems with diffraction gratings. I'm going to talk you through the math and strategies involved. So let's go ahead and get to it. All right, so this is another diagram I've created, and there's a lot going on in this slide. So again, I'm going to take you through this step by step so you don't get overwhelmed. All right, so incoming light rays right here, I'm showing them as rays, not as wave fronts as we have seen previously. And the reason for that is because they're going to continue through as rays as they go through these two slits. So there are two slits right here, and there's a distance between the center of both slits right there that we're going to call D. This is our front screen that's going to block the light. By the way, I should say for these incoming light rays, they're all of the same wavelength. So it could be something like laser light that's coming in. And what's going to happen is you're going to have a central maximum right here where you're going to have constructive interference like a bright spot or a bright swath of light right here. And then your next one up is going to be the first order maximum where you have another bright area up here. And this is our second order maximum where you're going to have a greater light intensity up here as well. We'll also have the same down below. I haven't shown those, but you get the idea. And in the middle, that's where you're going to have the crests and troughs of waves meet up. So you're going to have destructive interference here and here. So it's going to be alternating bright and dark spots, you could say. And so the question is why? Why are we going to have this alternating bright and dark spot situation? Like, what's up with that? All right, and that's where this diagram comes in. So this is like a zoomed in version of what's going on here. I'm going to say there's an angle involved, and so we're just going to have this angle. It's going to be measured to a horizontal line, let's say. And the geometry works out where this angle is actually equal to this angle over here. You can think of this as a right angle, and this is a complement to this, and so on. But these angles are actually going to be the same. Now let's say they're going to be firing off at some distant spot over here on the back screen, you could say. And if they fire off at some distant spot over here, they're nearly parallel to each other. They're not completely, but they're nearly parallel. And so the major difference for their length of travel is going to be this distance right here. This distance right here would be this d value times the sine of theta. Using geometry and a little bit of trig, that would be true. And so this is the length difference between these waves. Now, what if I were to say to you, all right, let's say these waves were off in terms of the length that they traveled so that now they are like 2 wavelengths off of where they were before. Will that make a difference? If this travels an extra 2 wavelengths right here for this d sine theta value, what do you think? Well, the answer is no, because what's going to happen is when they hit the spot over here, they're still going to be in phase. So they're still going to have a bright spot over here, let's say, assuming they were in phase before. All right, well, let's say this d sine theta value works out to be only like 1/2 a wavelength off. What would we see over here? Would we see a bright spot or a dark spot? What do you think? Well, if they're now 1/2 a wavelength off, then that means they're out of phase, right? And if these waves are out of phase when they hit their target over here, are we going to see a bright spot or a dark spot? What do you think? The answer is we're going to see a dark spot. Even if they're the exact same type of wave with the exact same frequency, wavelength, amplitude, wave speed, all of that, if they had been shifted over by 1/2 a wavelength because they had to travel this extra length down here, this ray had to travel this extra length down here, and now it's been shifted over by 1/2 a wavelength, that means they're going to be out of phase when they hit their target. All right, let me show you another example of what I'm talking about here. So this is basically the same diagram that I just made, but someone else has made this diagram. So if the difference in the path lengths that these waves travel is off by a wavelength or some integer multiple of a wavelength, like 2 wavelengths, 3 wavelengths, and so on, what's going to happen is it will end up with a bright spot or bright fringe, you could say. If it's off by some 1/2 a wavelength or some integer multiple of a 1/2 a wavelength, then you would see a dark spot or a dark fringe when they finally hit their target. And that's because these are going to be out of phase. And if you forgot what I meant about being out of phase, this is what I talked about with you. And if they're in phase, they're going to be completely constructive like this. All right, so let's go back to that image that I had talked about previously. What we can now do is we can now write equations for this. You could actually derive these equations if you thought about them hard enough. This distance right here, the difference in the path lengths of both of these light rays right here, if they are some multiple of the wavelength, you're going to get constructive interference going on. And if there's some multiple of 1/2 of a wavelength like shifted over, like an m value of 0 plus 1/2, let's say, then you're going to get destructive interference. Alright, I'm going to show you how to do this in a problem, but first I need to talk to you about one more thing because you will see it in problems as well. And these things are called diffraction gratings. So instead of using Young's double slit experiment, a lot of times we'll talk about diffraction gratings and you'll see them in problems. And they are very similar to Young's double slit. It's just that they have many, many slits. Diffraction gratings are fun to play with. There's a lot of different physics involved that you can do with them. But usually you're going to get a grating and you're going to get a value that's given to you by the manufacturer. Like this is 4,200 lines per centimeter. And that's all fine and good, but actually we need the distance between one line and the next for this equation that we just talked about. We need the d value, right? Between one line and the next. So how do we get that? We're going to assume one line. That's going to become our given. And then this really is a ratio, right? We have 4,200 lines per centimeter for this example. So we can come out with our answer. And then at the end of that, you'll have to convert that to meters almost certainly as well. But that's how you would do it. And I have no idea what this language is, but I think the image is actually really helpful to understand what we mean by a diffraction grating. Alright, so let's look at an example problem. So it says a diffraction grating with 2,100 lines per centimeter is light that has passed through it of 572 nanometers. What is the first and second order maxima angles? What is the first and second order minima angles? Alright, the first thing we can write down is this given value in nanometers. And nano means times 10 to the negative ninth. So we're talking about stuff that's very, very, very small. And what else can we do with the problem now? What can we do to begin the problem and put this word problem into terms of physics or of math? Well, we can do what I just talked about, and that is know that we are given a problem that's talking about how many lines per centimeter we have for a diffraction grating, but we need to know the distance between one line and the next. So if we assume one line, that becomes like our given. We multiply it by this ratio right here, and that should be our d value. So I should say like equals d. One more thing with that is that we will need to convert that into meters as well. And then we should update our values over here. So I did use d is equal to our answer. All right, let's clean some of this up. I need more room to be able to do this problem. So let's do part A. Part A says, what is the first and second order maxima angles? All right, so we're looking for an angle right here. That's going to be our unknown. So algebraically, let's go about solving for that. If you want to pause right now and do that yourself, go for it and see if you come up with the same thing that I do. This first step is easy, right? Sometimes students stop here, but we're not looking for the sine of theta. We're actually looking for theta. So how do I get rid of this sine function right here? Well, I'm going to use the inverse sine function of both sides. If I do that, this sine cancels out. I'm left with theta is equal to the inverse sine of this over here. And now I'm ready to plug in my values. And if I'm talking about the first order maxima, not the one in the center, but the one that's slightly like the first bright spot, you could say, then that m value is going to be 1 right here. We do the math, and it turns out to be this answer right here. If we do it again for the second order maximum, we end up with this answer right here. Now it's tempting to just think that these are actually double of each other with like rounding errors or something, but that's not the case, so be careful of that. All right, let's take a look at the B part of the problem. What we're going to do is now look for the first and second order minima angles. All right, so let's go ahead and do that. The only difference with this equation is we have to offset it by 1/2 of a wavelength, essentially. And one other key difference is that we're going to start with a 0 value for m if we're talking about destructive interference, if we're talking about the minima angles, because remember the very center is going to be a bright line, and the next one up from that is going to be the first situation. And that bright line had an m value of 0. So we're going to go ahead and plug in our numbers at this point because we're now ready to. Notice what I'm using for my m value right here because I want them to be offset by 1/2 a wavelength. And then I do the same thing for the second order minimum and get my second answer here. And that's it. That's how you do one of these problems using these equations. And I do want to talk about one more thing. There are two topics that this lesson naturally leads into. And they're both important, but they're not like stuff that has to be covered at this moment for a physics class. They're just cool. I would say they're super important. but we have other topics to get to at the moment. I may come back to this later, but these topics are so cool, I just want to point it out before I move on and do other topics. Spectrometers. You now can understand how spectrometers work. And spectrometers are crucial for chemistry as well as biology and really for astronomy. If you've ever wondered, how do we know what a star is made up by? Like, what elements of plasmas make up a star? Well, you have to understand how a spectrometer works. But now you can, because now you know enough background about how diffraction works and so on to be able to understand how a spectrometer works. Maybe I'll put a link down below so you can take a look at it. It's really cool stuff. And secondly, I've talked to you about waves and how they interact with the double slit experiment, but it gets super crazy and weird if we take something like a beam of electrons and do this, because if you think about it, electrons, we've thought of electrons as particles, right? Of course they are. They're like little negative charge carriers that orbit an atom. And so of course they would behave like a particle, right? Well, the answer is it's really complex, really cool, and really weird. Now you can take a look at the wave-particle duality of quantum physics using the basis of Young's double slit experiment to learn something really crazy. So I'll put a link down to a good lesson on that as well. And maybe I'll do my own lesson on that as well as I get more time. In any case, I hope this has been helpful. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.